Hello fellow skeptics, I'm Luther Name, and this is the 20th video in a series of videos addressing the broad topic of, is something wrong with physics, modern physics perhaps? If so, what? And can it be fixed? And it turns out it's just more than just modern physics. It also goes back into classical physics. In the last several videos I've addressed the issues related to relativity and culminating in a discussion on general relativity. And the interesting thing about general relativity is that Einstein's equation is correct. It's a good generalization of what's called the Euler-Lagrange equation. Problem, as I pointed out, is we put the wrong stuff in it. You get the wrong stuff in it, well then you get the wrong stuff out. Garbage in, garbage out. And you take a perfectly good equation and then you put approximate values in. The inverse square law, point mass, all those types of things that are just not true. They're approximations, simplifications. What you get is a wrong answer. And as I've mentioned before, general relativity of the equation breaks down just where Newtonian physics breaks down, in close proximity. If you use Newton's general equation to describe the interaction with a gravitational and even electrical interaction, why, what you find is that you can have different relationships among interacting objects when they're in close proximity. Not the least of which, at least from the respect of measuring orbits and what have you, which is what the Euler-Lagrange equation is very good with, you have a different form of the orbital angular momentum. And that clearly makes a massive difference, or can make a massive difference in terms of interactions of objects when they're in close proximity. So our classical approach to such things is wrong, and using these same approaches in Einstein's equation gives the same erroneous results. All solutions that I've seen, at least that I can understand, of Einstein's equation relate to orbits. And so that's a two-dimensional representation, and as a result, the Einstein's equation reduces to the Euler-Lagrange equation with a perturbation. The perturbation is associated with the Lorentz metric, and that extra term of time is the fourth dimension. So we know how to do that. In fact, we can arrive at those same types of equations with the same types of perturbations, as I pointed out in the last video, using Newtonian physics, the correct Newtonian physics. But we couldn't do it until the modern era of computers. It was impossible to do these kinds of things. I mean, quite impossible. And the interesting thing is that if you move forward into quantum mechanics, where you've got solutions to problems using Feynman diagrams, they talk about solving thousands of Feynman diagrams in order to basically understand certain types of... You can't do that. That's a fool's errand. While it may be on case by case an interesting exercise, you can't have a theory based on that kind of thing. So there's something wrong. There's something fundamentally wrong with that type of formalism. But that's for the future. Right here, what we're doing is we're wrapping up the issue with respect to general relativity, with respect actually to the whole first 20 videos, which is something wrong with physics. The answer is, yeah, there's something wrong with classical physics. There's something wrong with modern physics in how they are replicating and advancing what's going on with Newtonian physics. And we have these reformulations, starting with Lagrange and then going into Hamilton, and then actually Einstein was reformulating classical mechanics, and these are all legitimate efforts. What you'll find is that actually quantum mechanics is the same thing, because Hamilton had a hand in developing a Hamilton-Jacobi equation. The Hamilton-Jacobi equation is the underpinning to quantum mechanics. And so you have this natural evolution that quantum mechanics is actually a reformulation, in a way, of mechanics, of classical mechanics. Even though we talk about general relativity and special relativity, or the restricted theory, as being modern, they're still related to classical mechanics, because the Euler-Lagrange equation itself defines paths, geodesics, optimum paths optimal lowest energy paths within various spaces and surfaces and descriptions. So what you have is a perfectly good path that is now laid out. All I did was go back to the books and say, oh, that isn't quite the right interpretation. Oh, we missed this. Oh, we should be doing that. Because look, he says this, but we didn't do it. We made assumptions. And all I've done is lay out some breadcrumbs. There's nothing new in the physics I've done. What I've done is I've highlighted existing physics, physics that everybody knows, but they haven't thought to apply to a common set of problems. The question that hasn't been asked, or I haven't asked it to this point, is, so can physics be fixed? And the answer is, yeah, we can make an attempt to fix it. The question is, who's going to fix it? That's the issue. Who can fix it? I don't believe academia can fix it. I think they're incapable of fixing it. I don't want to get into the sociology of how our academic institutions evolved, but they have evolved. We have adopted some things from the European universities and brought them over, but we added on to it a thing called tenure. And tenure has basically first forced us to over-specialize on the one hand, and on the other hand is basically removed all accountability from the academic environment. You got tenure, well, you don't have to be accountable for anything. Well, that's absolutely wrong. And all the great progress that was made, certainly in physics and in other areas, in the European school universities, were made without tenure, because the people had to keep producing. They had to be active. They had to be productive. So we've lost that train, and we've forgotten that was the case. We've basically allowed our academic environments to become isolated and to be insular. I could see it happening back when I was in graduate school, that there were some trends. And it's been noted by people such as Sean Carroll. I'll pick his name for a particular reason. I've heard him lecture. He's very interesting. And he gives a good talk. But I'm not sure I believe everything he says. But I'll get back to him. What you have are these people who will admit that things have gone off the rails in physics 40 years ago. Well, I believe in physics anyway. I'm not sure about some of the other areas. What happened was we began to strip applied physics out of the physics departments. There was a slow process that started after World War II and up through the 60s and 70s where there was a lot of applied physics. And physics departments, academic physics, had a lot of people doing applied work. In fact, interestingly, in electrical engineering and mechanical engineering, there was a lot of applied physics going on, and even in these areas. There was a great breadth of research activity and looking into phenomena that had just been exposed in the technological efforts. I would say not the only one, but one of the more prominent was at the radiation laboratory associated with MIT, the RAD lab. And what they did was they produced I think it was a 30-volume set of writings that basically codified a great deal of the kinds of research that they'd come up with, applied research, taking science and applying it to technology, and they wrote books. And these books were then made available across the United States. They weren't classified, so anybody could get them. The effort was to populate our universities in the technical areas, in the science areas, with a common knowledge base of newly found things, a new way of thinking about solving problems. And there was a lot of book writing going on at that time. But I noticed about 40 years ago that books began to get to be overly complicated. The ones, and I pointed out a few in the prior video that I used, what happened was the authors began to posture for their peers. Posture for their peers. It's a good one. And they made things more complicated, elegant. And they made it almost impossible to go through. And I began to see that new books that were coming out in the 70s and on into the 80s were overly complicated with what they they considered mathematical rigor. Rigor where you didn't need rigor. What you needed was competency. What you needed was a way to do it. What we used to call doing story problems. Well, they're really setting up scenarios. What you needed was a way of addressing problems and then doing problem solving. And physicists have always played short shrift. I mean, the renormalization in field theory is a prime example. What the hell is it? It took 50 years for anybody to say, well, I guess it's a legitimate process itself. Well, it turns out the equations are not right. But if it works, it works. Hey, we got a problem with the mathematics. Well, let's solve it this way. So physicists have always played a little loose and fast with the application of mathematics. But what you began to see in the 70s and 80s were these books that were being written with mathematical rigor. And there were too much rigor and not enough attempts at doing working with scenarios and solving problems. So starting about 40 years ago, you began to get applied physics being stripped out of academic physics. And so they became isolated, and you had these really high quality technology departments being formed, doing research that had heretofore been done within academic physics or other academic departments, and now they were being, with the people moved, they formed groups, and they would be solving these technology type problems. Physics, in particular, became barren of applied people, and then applied physics became anathema, and so it was given short shrift. So in a way, the academic physics has drifted into this theoretical world. And to get back to Sean Carroll, his namesake, Lewis Carroll, wrote about Alice in Wonderland. Well, in a sense, he's working in a wonderland. He's at Caltech, one of the premier universities in the United States for technology and science. But it's a wonderland. It's a land devoid of context with reality. There's a problem. What is the problem? Well, they can't articulate it. Well, there's a problem. How are we going to solve it? Well, we got to find a problem. As Einstein so famously said, you got to ask the right question. And they don't even know the question to ask. So a lot of what I've been trying to do here is, here are some of the questions to ask. But I'm not sure that the physicists, the physics community, the academic physics community can do it by themselves. I think they've got to be taken by the scruff of the neck and basically pointed in a different direction. Max Planck, first Nobel laureate, opined, you never really change the minds of many people. He probably pointedly referring to his own physics peers. You wait for them to die off, to leave, and the new people come in who are more flexible and willing to accept the new ideas. And I think that that's exactly what's going to have to happen. We're going to have to basically gut our current programs and the people who are basically guiding them. If this large body of excellent people, smart people, can articulate the problem, can articulate potential solutions, and have missed all the things that I've identified. I mean, the things that I've identified are things that I noted as oops, when I would be reading a book or solving some problems. So why is that? Who came up with that? Why did they do it this way? I was always asking those questions. And so here I am at this particular point, having taken the opportunity to dig into it. And once you start to dig into it, it just, the barriers and shells and everything begin to fall away, and you begin to see the inside core of things. As I mentioned before, I made a stack of yellow tablets, going through and doing calculations. And at some point, I finally said, I've got to codify this in some sort of formal way. So I wrote some books, and really a conversational way of organizing and codifying the kinds of things I was doing, putting them in order, because my approach is not necessarily strictly in order, and so I had to come up with an order of doing things. So I put them together and published some small books on various topics that I've covered within these videos. Sole purpose of these books was mostly for myself. And if I wanted to talk to somebody, I said, well, here's what I'm talking about. So, and I think we need more of that. You know, the old timers used to do that. Some of their papers were written in a very nice conversational style, but we've also gotten so formal, you can't understand what they're talking about. And again, you have these publications, and you've got gatekeepers, and the gatekeepers are not very good. I think that most of the prominent people, they get so busy that they have somebody screen things for them. Who should I talk to? What should I read? This kind of thing. Here, gatekeeper, go ahead and help me out. Now, I'll pay you so much an hour for your efforts. And they're not very good. And so what we have is really, they're hacks. And we have gatekeepers, hacks, who are basically screening things. And so who does an academic talk to if he wants to get a new perspective? I mean, even the various areas of the government involved with technology, NASA, DARPA, Department of Defense, other places, will occasionally have workshops in forum. What do? Well, they invite science fiction writers. They invite people who can think outside the box, but aren't necessarily constrained by peer pressures associated with, well, that's not the correct physics. Well, that's not exactly correct. People sniping at them all the time about this. Hey, what about this? And so what you get is new ideas, fresh ideas, and fresh approaches. And that was one of the strengths of the early Jasons. And you can look that up. Finkbeiner, I think is her name, wrote a book about Jasons. And it's worthwhile taking a look at it. I think she got a lot wrong in terms of what she says and the motivation, but it's an interesting story in that it's been known that you got to have people who know how to solve problems, but they have to be in an environment where they're not being intimidated by their peers or anybody else. Classical problem solving techniques that grew out of the Cold War era, the Delphi method, other methods of how you get new ideas and fresh ideas. And I think that that's the problem in academic physics, and maybe the problem in academia. You can't discuss ideas when you have peer pressure from people who can exercise authority over the individuals. You don't get free thinking, you don't get broad thinking, and I think that that's one of the basic issues. I think that we've got to remake academia. Without that, we're not going to get anywhere. So, who can solve the problem? I think that somebody who is involved with funding, and the problem with people who are involved with funding, oftentimes they're groups within the government, and they're populated by academics who are either on sabbaticals or leave academia and come there, and so they're not exactly free thinkers. They're still encumbered by the old ways. So we need to have a way of inculcating a broader range of thought and funding of ideas. We used to do that, and we made amazing progress. The sweet spot we had during the 50s and the 60s, and even up into the early and mid-70s, the technology that we spawned was based on the fact that, hey, let's see if it works. Let's try something out. I know it sounds goofy, but hey, it seems to me it might work. Let's look at it. A lot of it did. A lot of it did. I was involved with a lot of ideas, evaluating them from places like DARPA or what have you. They sounded good on the surface. When you peel back layers, and no, yeah, first blush it's good. Second and third blush, it's got problems. So, advanced technology, we went through a sweet spot, and then we abandoned it for political reasons, mostly for political reasons. So, with that, I'm going to conclude this. I'm going to get into quantum mechanics. I'm going to apply some of the same techniques with quantum mechanics as I had with looking at classical mechanics up through special relativity, and to see if I can find where we have done the same thing by making assumptions or doing simplifications and then forgetting we were doing those simplifications, to see if I can understand a little bit more I want to get to where Schrodinger's equation is, and maybe the Schrödinger equation isn't the end-all be-all. I know we got the Hamilton-Jacobi equation, and I know that there are many elements of that that are similar to the Euler-Lagrange equation and Einstein's equation. There's a relationship among them. These equations are all the same form. They're based on calculus of variation and finding minima and extrema. So I'm going to take a look at that. And that's it for this. Again, I'm Luther Name. Leave a comment. Show this to your favorite academic and see how they react. And I'll see you later in video 21, which will be the beginning of my investigation into quantum mechanics.